Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we're continuing our study of amines, and we're going to review a topic we covered back in alkyl halide chemistry. Now, this topic is referred to as Hofmann Elimination. If I flip back in my notes and take a look at elimination mechanisms in in alkyl halide reactions, I can find on page 55 of the alkyl halide section of notes the discussion of the Zaitsev rule and Hofmann elimination. Now, what's interesting is if I go down in the notes to the third item in the list, the third item refers to what are called bulky leaving groups. Okay? Bulky leaving groups. Now, this third category of bulky leaving groups utilized the example of a quaternary nitrogen. And in fact, when we covered it in alkyl halides, we actually said not to pay too much attention to it until we covered amines. Well, now that we're doing amines, we can take a close look at this, and we're going to actually come to that reaction. Now, it turns out that elimination is not really an issue if we look at one of the simplest of the quaternary nitrogens, and that is Tetramethylammonium Chloride. If I take a molecule like Tetramethylammonium Chloride, such an ammonium salt is positively charged. The nitrogen bears a positive charge and Cl bears a negative charge. Because it's an ionic salt, ion exchange is very easy to carry out. And if we want to trap out the chlorines, we can use silver ions to remove the chlorine. So we can take silver 2 oxide, react that in water. Silver halides are not water soluble, and so they precipitate out. And if you apply heat to this, the silver will trap out the chlorine and you will do ion exchange. And you will produce tetramethylammonium hydroxide. Now, there's no threat of elimination reactions in this salt because you need at least 2 carbons to make an alkene, and with the methyls off nitrogen, there's only 1 carbon. So you very readily can make this type of ionic system. But let's go back to the alkyl halide section and look at that example of the bulky leaving group. Take, for example, CH3 3 times nitrogen, then have the nitrogen attached to a sec-butyl group. So it's positively charged. And examine what would happen if we had the hydroxide anion with this cation. Or, if you like, NNN trimethyl sec-butyl ammonium hydroxide. The methyls are not affected by the presence of hydroxide, but hydroxide is a base, and bases can remove protons, allowing substituted alkanes, such as alkyl halide, so in this case it's ammonium, to undergo elimination reactions because the N plus CH33 is a good leaving group. If we undergo E2, I can envisage two pathways. That is, I can draw two transition states. Where my base goes for different protons. If you like, I can either attack the H on the CH2 or the H on the methyl. What would that transition state look like? Well, if I draw a transition state, take some time to draw this. And let's use bond forming this time. It's red and bond breaking as black. So we're pulling off an H. Okay. And we're pulling off actually you don't need quite that long. Our NCH3. Three times, and we'll have a CH3 here. So there we go. Black. So the black bonds are breaking. We have a few more groups to draw. We have an H here. And we have an OH here. Nitrogen is delta plus. This oxygen's delta minus. So red is bond forming. And black is bond breaking. So bond breaking and bond forming. And if we continue with this elimination, we get CH3, CH, double bond, CH, CH, three. We end up with 2-butene. However, I can likewise draw a transition state, another transition state, CH3, CH2, CH, N bracket CH3 three times. We have a bond to a CH2, and we have an H up here, and we can have the OH here. And we can draw in our bonds. Again, bond breaking. E2 gives me anti-periplanar elimination. Red will be bond forming. So we have bond forming. Yes. And we have bond. Let's put in our delta minus. Delta minus here. Delta plus. As the electrons are transferred to the hydrogen, the positive charge on nitrogen disappears and the negative charge on the oxygen disappears, effectively canceling each other. And we have bond breaking. So there we go. Now we finish off with transition states. And the double dagger here, always remember, means transition state. So those are two transition states that are possible. In this case, we get CH3, CH2, CH, a double bond, and the CH2. And what we have here is 2-butene forming and but-1ene. There you go. I named it both ways. Now what's interesting about this elimination is that the leaving group, the trimethylamine that's being kicked out, okay, we're kicking out in both cases an NCH3 3 times. That leaving group, right, is bulky. And because of the bulky methyls attack of these H's is more difficult. And it's reduced. As a result, only 5% of the more stable 2-butene is made or isolated. Now it's more stable because it's a more substituted double bond. But if hydroxide can't get at the hydrogens that are red here to pull them off, then you're not going to make 2-butene. You get 95% of 1-butene. 95% of 1-butene. So Hofmann elimination can occur in quaternary ammonium chemistry, especially when you make these ammonium hydroxides. These quaternary ammonium salts, though, are far more important than just in the dealing with Hofmann elimination. And they're crucial for something referred to as phase transfer catalysis. Phase transfer catalysis. And if we're going to look at phase transfer catalysis, to understand why it's necessary, let us review an older chemical reaction. That is what happens when you take cyclopropane, not cyclopropane, an alkene, such as, I don't know, let's just use ethene. And you react it with CHCl3 and hydroxide. Now we learned that CHCl3, and this was last semester, reacted with hydroxide to produce carbanion. Now carbon's not at all acidic, but you do get some trichlorocarbanion. And the reason for this is the very electronegative chlorines stabilizing the negative charge. We also learned that trichlorocarbanion would fall apart to Cl- and dichlorocarbene. Now dichlorocarbene could react with the alkene. So CHCl3 hydroxide formed dichlorocarbene, and what would happen is the carbene would add to the alkene to produce a cyclopropane, and one of the carbons would have two chlorines off of it. We learned this last semester in alkene chemistry as a reaction of alkenes. But there's a fundamental problem with this reaction. What is that? Alkene is organic. Chloroform is organic. Both molecules are significantly soluble in the organic solvents, but not soluble in aqueous solvents. On the other hand, hydroxide is polar, capable of hydrogen bonding, and ionic. It's not soluble in organic solvents. It's only soluble in aqueous. So hydroxide is only soluble in aqueous. Chloroform is an organic solvent, not soluble in water. How is it possible for the two to react if they cannot meet each other? They cannot cross the aqueous-organic phase boundary. Clearly, no reaction can occur unless this problem is solved. And this problem is solved by using phase transfer catalysis. So using this organic reaction, let's take a look at phase transfer catalysis, if we can. All right. Phase transfer catalysis is a procedure that uses two immiscible phases which are in contact with each other. So you'll have an aqueous phase and an organic phase. The aqueous phase will possess the ionic reactant, and the organic phase will possess the organic substrate and organic reactants. Now, reactions between the two phases are normally inhibited due to the lack of solubility of the reagents. They can't come together. However, if we use a phase transfer catalyst, something that looks like this. Let's put a benzyl on the nitrogen. And then let's add some ethyl groups. In fact, let's add 3 ethyl groups. And because it's quaternary ammonium, there needs to be a counterion, and let's make that chloride. I'm going to let this molecule be symbolized by Phi plus X minus. If I was to name this salt, I'd have benzyl triethylammonium chloride. benzyl triethyl ammonium chloride. Okay. Now, what's interesting is this molecule is ionic, positive plus minus. Because of that, it has some limited solubility in water. In water, the ions would dissociate. The chloride will be solvated by water molecules, and the positive ammonium salt will be solvated by water molecules. On the other hand, the organic nature of the benzyl and ethyl groups make this molecule significantly soluble in organic solvents. The only difference is in the organic solvents, the chloride will stay closely associated with the positive, forming a complex ion, overall neutral, and the organic ends will solubilize this material. Because of this, essentially, the phase transfer catalyst acts as a transport agent for the reactants across the phase boundary. Let me show you what I mean. Remember the previous reaction where we generated dichlorocarbene? We had to get hydroxide to react with chloroform, CHCl3. Well, this phase transfer catalyst would allow that. How? Suppose I threw in my reagent sodium hydroxide and water. So here's my sodium hydroxide. And I'm in aqueous solution. To this solution, I add some 5 plus X minus. Now this material is soluble and will establish an ion exchange equilibrium in which we form sodium plus X minus plus 5 plus OH minus or HO minus. Now this is an aqueous solution, so I'm going to draw a line across here, and this is going to represent my phase boundary. I have aqueous here, and I have organic here. Now, the 5 plus HO minus, because it's organic soluble, will be in equilibrium with 5 plus OH minus in the organic layer. And there will be some distribution coefficient, some solubility factor, if you like, between the two layers. Now, I can react this base with CHCl3. CHCl3 will come in, being in the organic layer, CHCl3. And it will get deprotonated, forming 5 plus CCl3 minus. And you'll get H2O forming, which is not soluble in the organic layer, will phase separate and rise to the organic layer. Now notice I put the aqueous layer on top because chloroforms typically are more dense. Chlorinated hydrocarbons are typically more dense than water, usually on the bottom. Now we learned that the trichlorocarbanion falls apart. Okay. So the trichlorocarbanion falls apart, and we get CCl2, our dichlorocarbene. Of course, that would form Phi plus Cl minus. Now Cl minus was our X minus, so that's in equilibrium. the 5 plus Cl minus in the aqueous layer is in equilibrium with the 5 plus Cl minus in the organic layer. And you see we've established a cycle. The dichlorocarbene that forms now, of course, can react with our alkene as it forms, that's present in the organic layer, and that will produce our dichlorocyclopropane. So essentially, the 5 plus X minus, our phase transfer catalyst, acts as a transport agent, carrying hydroxide into solution and removing chloride out of solution. And the cycle will continue as long as you have reagents available to react. Now, phase transfer catalysis is a reaction that can accelerate two-phase reactions by a factor of 10,000 to 1 billion times. That's significant. 10,000 to 1 billion times faster than in the absence of such a phase transfer catalyst. It can effectively make a reaction that's not occurring happen. One important condition is increasing the surface contact between the two phases at the boundary. This can be done by agitation or shaking. Shaking or agitation maximize surface contact, causing efficient exchange of the phase transfer catalyst. So quaternary ammonium salts have very important chemistry. Not only are they involved in the Hofmann elimination, allowing you to get the less stable alkene as a predominant compound, they allow you to do something called phase transfer catalysis. Okay. The next section we want to look at are important or biologically active amines. Now, some of the structures I'm going to draw biologically active amines are rather large structures. Not all of them are. And while you should be able to draw them, I'm not going to insist that you can. But I do expect you be able to recognize them and name them. And in the names that I give you, you can give me either name. I will expect you to be able to provide one use or effect. Now, I'm not going to write out the use or effect, but I will talk about them once they are drawn. The first thing I want you to note is that many of these biologically active amines are based on this structure. An aromatic ring, an ethyl, and an amine. A large number of these biologically active amines consist of this beta aromatic ring, ethylamine. Many of the structures. In fact, if I take this structure and modify it, I can produce our first two biologically important amines. That is, put a couple OHs off our aromatic ring. Put an OH off our ethyl. NHCH3. And here you have the molecule adrenaline, which can also be called epinephrine. both names are acceptable. Under use or effect, adrenaline epinephrine is a hormone which is released into the blood and causes increased blood pressure, widening of the lung passages, and increased heart rate. So increased blood pressure, widening of the lung passages, and increased heart rate. All of this is to prepare the animal to fight or flee. Epinephrine is often added as an ingredient to local anesthetics used by dentists, such as Novocaine and Lidocaine. The reason for this is these compounds tend to slow the heart, causing a drop in blood pressure, and a tiny amount of adrenaline, has to be very careful, is added to increase the heart rate, to compensate. Noradrenalin is very similar. If you compare the two structures, noradrenaline is a very similar compound. Noradrenaline has the same hydroxy structure that adrenaline has. Its only difference is that it lacks the CH3 off the nitrogen, so it is an NH2. And it's referred to as norepinephrine or noradrenaline. Noradrenaline or norepinephrine. Like adrenaline, noradrenaline is a hormone which causes increased blood pressure. It's also involved in the transmission of impulses from one nerve to another. Now, if we remove the OH, off the ethyl, if we just put a CH2, NH2, we have the molecule dopamine. Dopamine is a neurotransmitter connected with motor control and motivation. It's connected with neural disorders, such as Parkinson's disease. Now, if we change the aromatic ring, but keep the ethylamine of dopamine, we can produce another neurotransmitter. If we use a rather large aromatic side chain, so we have a benzene ring, we have an OH here, and then we have a 5-membered ring with the nitrogen, here. This is an aromatic system, and then we attach here a CH2, a CH2, an NH2. We have the molecule serotonin. Serotonin is another neurotransmitter. So if you like, dopamine and serotonin are both neurotransmitters, but serotonin is connected with regulation of sleep and wake cycles and the maintenance of stable neural processes. It's suspected that improper metabolism of serotonin may contribute or play a role in schizophrenia. Now you'll notice these all have aromatic ethylamines. It turns out if you take the ethylamine and put methoxy groups on it. In fact, 3 methoxy groups. You'll notice that all of these ethylamines play some role in neurotransmission. They act as neurotransmitters, that is, they affect the brain. So it's not surprising to find that there are structures, such as this molecule, which is called mescaline, which is a powerful hallucinogen. Produces hallucinations. Presumably directly related to this ethylamine structure that's very related to these compounds, dopamine, noradrenalin, and adrenaline. Another biologically active amine that does have some ethylamine relationship in its structure but we add a methyl off the alpha carbon. If we do that, we have a molecule called amphetamine. Amphetamines are powerful stimulants. They're used in the treatment of narcolepsy. That is, individuals who can fall asleep mid-sentence during a conversation. And they can also be used in the treatment of attention deficit hyperactivity disorder. Amphetamines are powerful stimulants and act on the brain. Another addictive stimulant that is found in small quantities in tomatoes, potatoes, eggplant, green peppers, but in larger quantities in tobacco, is this molecule. And this molecule is nicotine. Nicotine is an addictive stimulant that, as I said, is found in the tobacco plant. It's also found, as I said, in small quantities in tomatoes, potatoes, eggplant, and green peppers. It's utilized as a substance to which people can become addicted, and is found in cigarettes. What's interesting is, while nicotine is addictive and generally thought to be a non-beneficial compound, nicotinic acid also known as niacin. This is an important B vitamin. It's one of a group of molecules referred to as vitamin B3. Its name is nicotinic acid or niacin, but is an example of a vitamin. Derivatives of this vitamin play key roles in energy metabolism in the cell and aid in DNA repair. Another pyridine-based vitamin is this molecule. And we're going to put CH3 here. We're going to put a CH2OH. CH2OH. And an OH. This is Pyridoxine. An example of a B6 vitamin, or vitamin B6. Pyridoxine vitamin B6 is a vitamin that contributes to the health of your cardiovascular system. It's connected with the balancing of sodium and potassium and is involved in red blood cell production. Now the next few molecules are rather large, so we need some space to draw these. The first one, and these molecules really are the reason I am making this section recognize only. I'm not going to make you have to draw these. So it's a CH3 here. We have two CH2s and an OH. Off of the end we have a CH2. And off of here we have an aromatic ring with a nitrogen, a nitrogen. There we go, an NH2. CH3. And you notice, if you look carefully, all the nitrogens have 3 bonds except this one. This guy's 1, 2, 3, 4 bonds, so there's a positive charge on this nitrogen. And we've got Cl-. This molecule is thiamine chloride. Thiamine chloride is vitamin B1. It's a vitamin whose derivatives are involved in the metabolism of carbohydrates. Another interesting molecule that's very large is this molecule. Need more room. Okay, I think I've gotten everything here. This molecule is quinine. Quinine is a drug used to treat malaria. It was superseded by chloroquine, but the rise of chloroquine drug-resistant strains of malaria has caused quinine to start becoming the drug of choice for treating malaria. Once again, shows the overuse of these drugs can breed resistance, and often you have to fall back on compounds that were less used. Now, another ethylamine derivative that has an aromatic attached to it is this molecule. So there's our ethylamine, and we have this aromatic ring. Nitrogen's on it. This is histamine. You may be familiar with the term antihistamine. The reason that term is used to refer to fighting, sneezing, coughing, swelling, that type of thing, is because this compound is the culprit that produces those effects. Histamine is a protein-bound toxic amine found in most tissues. Its release causes symptoms typical of an allergic reaction. It could be swelling, reddening of tissues, runny nose, sneezing, red eyes, that type of effect. Of course, that leads us to the molecule that is a standard antihistamine. And let's try drawing that. We'll leave histamine up here. We'll just get rid of quinine. Okay, so let's draw. See if we can draw this. CH. CH2, CH2, and CH3 twice. And what you see here this molecule is chlorpheniramine. Chlorpheniramine is one of the first generation antihistamines used to prevent symptoms of allergic reactions, and it is a constituent in most cold remedies. So histamine produces allergic reactions, chlorpheniramine helps inhibit them. Another interesting large molecule that is based on amine chemistry we have O. Come down to this, another N, and then a double bond. And there we go. And an aromatic ring. Alright, and there's a CH3 off this end. So we have an amine in a ring here. This molecule is known as Valium. It's also called Diazepam. Diazepam. Diazepam is a drug which is a benzodiazepine derivative. These molecules serve as sedatives and tranquilizers and are used as antidepressants. Now I want to next show a class of compound where fortunately I only have to draw one structure and then make modifications to it. This is a structure that has significant biological activity, and it is based on amine chemistry. I'm going to draw a bond here that sticks up and above. Actually, go this way. So we have this structure. There's actually an H sticking up here. It's often shown in these structures. Double bond here. Aromatic ring up here. And we often have down here is an oxygen, which is linked to that because it's aromatic. There's no up or down there. This OH is down. And there's an OH off here. Yes, that's it. This molecule is morphine. Morphine is a highly addictive opiate analgesic drug. It is a great painkiller, but it is addictive. It's the active agent in opium, which is harvested from the seed pod of certain varieties of poppy plants. Morphine is used in hospitals as a painkiller. A slight modification to the structure of morphine, changing this OH to a CH3, produces the molecule codeine. Now, codeine is a medically prescribed drug for the relief of moderate pain and cough suppression. Compared to morphine, codeine produces less pain-killing effects, less sedation, and less respiratory depression. It's usually taken orally. The studies upon which cough suppressant activity have been investigated can be best described as highly debatable. Whether codeine really produces this effect or whether it's a placebo effect is debatable. Now, of course, if we replace the hydroxy groups of morphine with reacting with acetic acid to make acyl ester, as we put these acyl ester groups here, at both ends. You have the highly addictive molecule, heroin. And thus all the TV shows based on a shipment of morphine that gets lost and drug lords going after it and fighting it. Because it's fairly easy to convert morphine into heroin. Heroin is an illegal, highly addictive drug. It is both the most abused and most rapidly acting of the opiates. Heroin is processed and produced from morphine. Now, a molecule that I'm going to draw this structure again because it has quite a few changes from morphine, codeine, and heroin. It stands out quite a bit. So again, NCH3. There we go. And we'll put an OCH3 off here, so it's related to codeine. Codeine had the OCH3, remember? This is the molecule Dextromethorphan. See, codeine is a prescription cough suppressant, but dextromethorphan has been sold over the counter as a over-the-counter pharmaceutical for cough suppression. Dextromethorphan has been available as an over-the-counter cough suppressant since 1958. The advantage of dextromethorphan over those containing codeine is the lack of physical addiction, potential, and sedative side effects. Although, as with most cough suppressants, studies show that the effectiveness is highly debatable. Nevertheless, you can buy it and take it. And it's interesting to note that dextromethorphan, a cough suppressant, codeine, morphine, and heroin are all very related in their chemical structure. Only small changes can produce significant changes in chemical behavior in the biological system. Okay, well, there you have it, some biologically active amines. This brings us the end of our amine studies and the end of this Scribblecast. I'm Dr. Brian Lloyd. This is my Scribblecast lecture. I thank you for listening.